Energy. One very important concept in the study of thermodynamics is energy. Energy is a fundamental concept such as mass or force, and as is often the case with such concepts, it is very difficult to define. Energy has been defined as the capability to produce an effect. The first definition in this section. Energy is the capability to produce an effect. Capability an effect Fortunately, the word energy and the basic concept that this word represents are familiar to us in everyday usage. A precise definition is not essential at this point. Energy can be stored within a system and can be transferred. Energy can be stored within a system and can be transferred as heat, for example, from one system to another. For example, from one system in a study of statistical thermodynamics, we would examine from a molecular point of view the ways in which energy can be stored. Because it is helpful in a study of classical thermodynamics to have some notion of how this energy is stored, a brief introduction is presented here. Consider a system, a certain gas at a given pressure and temperature. A system at a given temperature contained within a tank or pressure vessel. Using the molecular point of view, we identify three general forms of energy. Molecular point of view, we have one, intermolecular potential energy, which is associated with the forces between molecules, between molecules, and second is molecular kinetic energy. which is associated with the translation velocity. This is associated with the translational velocity. Of individual molecules. Molecular kinetic energy. And 3 is the intramolecular energy. Molecular energy that within the individual molecules, which is associated with the molecular and atomic structure and related forces. Which is associated with the molecular and atomic structure and related forces. Three types of the energy using the molecular point of view. The first of these forms of energies, intermolecular potential energy, depends on the magnitude of the intermolecular forces and the position of the molecules relative to each other at any instant of time. It is impossible to determine accurately the magnitude of this energy because we don't know either the depends on the first intermolecular depends on magnitude of the intermolecular forces of the intermolecular forces. And the position of the molecules relative to each other at any instant. And the position of the molecules relative to each other. At any instant of time. As we said, it is impossible to determine accurately the accurately the magnitude of this type of energy because we don't know either the exact configuration and orientation at any time or the exact intermolecular potential function. However, there are two situations for which we can make good approximation. The first situation is at low or moderate densities. Good approximation. Low and in this case the molecules are relatively widely spaced so that only two molecules or 2 and 3 molecules interaction contribute to the potential energy. At these low and moderate densities, techniques are available for determining with reasonable accuracy the potential energy of a system composed of fairly simple molecules. The second situation is at a very low densities. Techniques are available for determining with reasonable accuracy the potential energy of a system composed of fairly simple molecules. The second situation is a very low distance. Under this condition, the average intermolecular distance between molecules is so large that the potential energy may be assumed to be zero. In this case, the potential energy assumed to be zero. Consequently, we have in this case a system of independent particles. A system of independent particles and therefore from a statistical point of view we are able to concentrate our efforts on evaluate the molecular, translational and internal energy. Only we have in this case translational and internal energy. The translational energy, which depends only on the mass and velocities of the molecules, is determined by using the equation of mechanics, either quantum or classical. The intramolecular internal energy is more difficult to evaluate. Let me write translational energy, which depends only on the mass and velocities of the molecules. It is determined by using equation of mechanics by using the equation of mechanics. Either quantum or classical. The intramolecular internal energy. Is more difficult to evaluate because in general it may result from a number of contributions is difficult to evaluate because in general it may result from a number of conditions. Consider a simple monoatomic gas such as helium. Each molecule consists of a helium atom. Such as atom possess electronic energy as a result of both orbital angular momentum of the electrons about the nucleus and angular momentum of the electrons spinning on the axis. The electronic energy is commonly very small compared with the translational energy. Atoms also possess nuclear energy, which except in this case of nuclear reaction is constant. We are not concerned with the nuclear energy at this time. When we consider more complex molecules such as those composed of 2 or 3 atoms, additional factors must be considered. In addition to having electronic energy, a molecule can rotate about its center of gravity and thus have rotational energy. Furthermore, the atoms may vibrate with respect to each other and have vibrational energy also. In some situations, there may be interaction between rotational and vibrational mode of energy. In evaluating the energy of a molecule, we often refer to degree of freedom of the molecules. And degree of freedom F of this energy for a monoatomic molecule such as a helium for monoatomic molecules F equals to 3 such as helium He. For a diatomic molecules such as oxygen F equals to 6 O2. These are the translation of molecules as a whole in the X, Y, and Z direction, and 2 are for the rotation. For the reason why there are only 2 modes of rotational energy is evident. where we take the origin of coordinate system at the center of gravity of molecules and the y-axis along the molecule's intermolecular axis. For a more complex molecule such as water molecules, for example H2O as the molecular of the water, there are 9 degrees of freedom F equals to 9. Most complex molecules such as typical polyatomic molecules are usually three-dimensional in structure and have multiple vibrational modes, each of which contributes to the energy storage of the molecules. The more complicated the molecules is, the larger the number of degrees of freedom that exists for energy storage. The mode of energy storage and their evaluation are discussed in detail in the Appendix C for those interested in further development of the quantitative effects from a molecular viewpoint. This general discussion can be summarized also that there are some definitions and books related to the molecular internal energies concept. The next discussion in this chapter is specific volume and density.